Okay, so the question that I asked before you went into breakout rooms was what species would I have in solution? And what kind of reactions do you think I have? And then we're going to rank things from greatest to smallest. So who wants to offer up what kind of species do we have in the solution?
I do.
Go ahead.
So are we including water or not?
Yep, all of it.
Okay, so we have water, sodium plus, F minus, HF, OH minus, and H3O plus.
OH minus and H3O plus.
Yeah, I said, did I say HF?
Nope.
Ah. Yeah,
cool.
I think there will be some.
Anybody disagree? Anybody have more? Good, I absolutely agree. So obviously if I'm putting it in solution, water is the solution. And what are my sources of OH and H3O plus, my hydroxide and my hydronium?
Wouldn't it be the water itself or the sodium and fluorine?
Okay. So absolutely, we have water itself. So we'll have from the water. And let's go ahead and write that reaction down. So I'm going to have my H2O going in equilibrium to OH minus plus H3O plus. Let's go ahead and balance that. Sweet. Does everybody see that? So this is the auto ionization of water. What other reaction do I have going on? Davey.
Could you do Na plus H2O? And then that would give you I know OH is in there, but I don't know what else.
So are you saying that this one would give me like NaOH?
Yeah.
And then like plus water?
Yeah.
Am I going to have a bunch of this or very little of it? Owen.
I'm sorry, what was the question?
Am I going to have a lot of this reaction happening when I put the sodium fluoride in my solution or very little of it?
You're going to have very little of it.
Cool. Why?
Yeah, because sodium hydroxide has a strong base.
Good. Fantastic. So if I have an ion that is an ion of a strong acid or base, I'm going to have very little, like imperceptibly little, because sodium is acting as a weak. It's accepting an OH. So I guess you could call it a base-ish. And that's because when we call something strong or weak, remember we're saying that it completely dissociates into water, or at least we would write like my sodium hydroxide and water, that are one of the few reactions that we would say is going to Na plus.
Wait, I thought acids were the proton donors, and
so is sodium accepting a proton or accepting a hydroxide? So remember, if it's an acid, it would be donating a proton. So it's accepting a hydroxide. We're actually going to come to a different definition of that with electron pairs and electron donors. But if I have, in fact, let's just leave this off.
All right.
We don't even need a definition for what it is. It's just going to be this sodium ion. Whoops. Why are we doing that? This sodium ion is not going to reform an AOH. So if I add something that is a strong acid or a base, so any of my halides in solution other than fluorine, they're not going to reform their acid, or any of my sodium, chromium, bromine, I'm sorry, barium, not bromine. If I add those to solution, they're going to stay as those ions because they form something that's strong, that's by definition, we write as just a single arrow. We don't write it as being in equilibrium. We're going to get such a small amount back that it's not going to change the pH if I add anything with sodium, chlorine, and all of those. Is everybody good with that? Okay, so I'm going to put a line through that. What else we got going on? What other reactions? Josh. Josh.
Not me.
Could you do NaF plus H2O yields HF and OH minus and Na plus?
Na plus HF.
Yeah, HF and OH minus.
Okay. Another way we could look at that is that I'm putting an ion in solution. So if I put that in solution, I'm going to have my NaF going into that. Yeah, there we go. I just wrote it out. What am I doing? I don't need to restate it twice.
So the Na would be the spectator ion in that case.
Yep. And so what does that make fluorine? So if I put just fluorine in solution, is fluorine an acid or a base?
It'd be a base, right? Because it's accepting.
Good. So it's accepting a proton to become the HF. So I'm just kind of writing this as an abridged reaction.
Okay.
That's what? OH minus?
Yeah.
Good.
So when we're talking about having the species in the solution though, do you need the full equation to be able to recognize that the Na plus would still be there at the end?
No, but it's good to remind yourself what ions actually are in the solution.
Mhm.
One of the more common things that I'll see is like if I do, can I think of something off the top of my head that has Cl2? I have like BaCl2. There we go. If I did like that in solution, what some students will do commonly is something like this. So part of the reason that I do the write your reactions, and that is not correct, by the way,
Right.
is to recognize what are your ions. So you get in the habit of knowing what those species actually are.
Okay.
And then it helps us predict what is actually going to be dominant in this. So now let's think about what we're going to have the most of. And I'm going to erase this over here. Okay, so what do I want to go? Let's go greatest. Of these species here, what am I going to have the most of? Let me pick somebody new. Rachel.
I'm not sure, but I would guess either the maybe the OH minus.
Okay, so why the OH minus?
I'm not really sure, but I know in a lot of the reactions the H3O plus or the OH minus would have like a larger concentration?
So what you're correct about is because I have this autoionization of water and fluorine is a basic reaction, my pH, the pH of this thing is going to be basic. I have two sources of hydroxide, so I know it's going to be basic. But say I have a liter of water. Do you think I have more hydroxide than I have water? Sarah?
I'm not sure.
Grace?
No, so I think water would be the greatest.
And you are absolutely correct. In fact, moles of water in like 1 liter of solution would be something like 50 moles is how much I'd be able to put in there. So I'm going to have the most amount in my aqueous solutions. Another way to think about it is the thing I didn't do is write aqueous below all of these, except for this one. Right, so the water part is most definitely dominant for my concentrations for the most of. Cool. What do we think next? Taking our water out. So we know it's basic. So I'm going to have some concentration of the OH.
I said the hydroxide anion, which would be the OH.
Okay. What about our sodium ion?
I think that would be slightly less than the hydroxide because there are 3 sources of hydroxide.
So careful there. I wrote this one twice. So these two reactions are essentially the same thing. So there's 2 sources of it. The
At least-
auto ionization, if this is room temp, is like 10 to the negative 7 molar of each of these guys. Right. So I added 0.5 molar of my sodium fluoride. So what is my molar concentration of sodium in this?
It would be 0.5.
Perfect. Yeah. So I know that this is going to be 0.5 molar, which is a lot bigger than my 10 to the negative 7. And I know that this is a weak base. So if it's a weak base, then it's not going to be contributing all that much hydroxide. It is going to change the pH, but it's not going to be a huge amount. That means that my 0.5 molar Na plus is going to be the next species that's dominant. Does that make sense to everybody?
Yeah.
Okay.
Makes
What-
sense to me.
Any questions on that?
Could you think about that as since the Na is not involved really in the reaction, since it's a spectator, it's just keeping its like molar concentration throughout?
Yeah. Yeah.
Okay.
Yeah. That is a very good way to think about it. What about my F minus? Do I have a full 0.5 molar?
I said no because there will be some contributing to the HF.
Yeah. So I don't know how much. I don't have enough information, but I know it's going to be less than the 0.5. But that still is going to be greater than the amount of hydroxide or hydronium because I'm starting off with this 0.5 molar. So I'm going to take some of that away and think about some of these Ka and Kb calculations you've done where we start with like 0.5 and we're like, can we ignore that minus X? And in a lot of cases we do, because the change to that is going to be relatively small. So I am going to have close to the 0.5, but not 0.5. So I am going to have this basic reaction going on. So now we have our sodium and our fluorine. What about hydroxide, H3O plus, and HF? Which one do you think is going to come next? Sean.
I think the OH would come next.
Perfect. Why?
Because it's a basic solution.
Yeah. Yeah, so it's a basic solution. We know that we are raising the pH and we have two sources. We have the autoionization of water and this weak base. So this is going to have my two sources, and that's why it's going to be next. What about my HF or H3O plus? Which one is going to be more dominant, the HF or the H3O plus, do we think?
I think the HF,
Good, why?
because the solution is basic and there was a initial 0.5 concentration of fluorine, and since fluorine would have a weak acid, there'll be some HF present.
Nope, you're absolutely correct. You're absolutely correct. So the only thing I have contributing to my H3O plus is the autoionization of water.
Yeah.
Right? My HF, if I'm making something basic, that means that I am contributing the HF in that reaction itself. So if my pH has gone up, that means I have that other species in solution as well. Now, what would be hard to do off the bat is to decide exactly which one of these, by how much they're going to be bigger. They're going to be relatively close in size, or I'm sorry, molarity in concentration, I should say. But it's going to be more or less in that order. These guys, this is like most definitely how they're going. How much different these two are, we'd have to do the math to figure that out. Are we good with that?
Yeah.
Okay.
Well, I am.
Any questions on that? This is one of your homework questions, goes into ranking how much of each species you have. And it's not asking for total amounts. This question is. So yeah, let's do one more breakout room on this. And then we're going to have some ADC questions after this, as we're going to talk about our ions in the solution. So take, I don't know, take 3 minutes on this. What I want you to do is write out your rice table and decide if we can use Ka or if we have to convert that to Kb, and how are we going to do that? Don't button push right now, just set it up. Is that clear to everybody? Okay. Now open up the rooms. I'll see you in 3. So 9:29.
I'm fine in 2 minutes.
How about 9:30? So what is the initial concentration of my fluorine ion? Let's start with our rice table.
0.5 molar.
Perfect. And do I include the concentration of my water?
No.
Good. No, I don't. So we're just going to put a line through that. And why don't we?
It's a different state of matter.
Yeah, so it's a liquid, it's not an aqueous, so we don't include that in our calculations. What about HF? What are we starting with there? Owen, what's my initial concentration of HF?
Well, I think it'd be 0 to start with.
And I would agree.
Yeah.
What about OH minus, Josh?
That'd be also 0.
Okay, what's the other possibility? Grace?
I am not sure.
Nikolai?
I am also unsure. I also would have said it was 0.
Well,
Would
no,
it be from water?
yeah, so
So 10
it
to the
might-
negative.
Oh,
it might be, but what we need to remember is that we have our water auto ionization, right? So I always have this going on where there's the little do-si-do between hydroxide, whoops, and hydronium in my water. But these concentrations at room temperature are this 10 to the negative 7. So they're relatively small. What we're going to assume is that we can ignore them. What we need to do is double check that our assumption is correct at the end. So what about my change? What's my change in fluorine? Is it plus or minus?
Minus X.
Good. HF plus or minus X?
plus.
Good. Yep. And it has to be, because if I start off, if I'm saying my starting point is 0, it can't go down. I can't have a negative concentration. So it has to be something like that. So I'm gonna have like my 0.5 minus X and my X and my X. Good. So now from lecture, I talked about when can we ignore this and how do we test that? When can I ignore the minus X? Alina.
So you can ignore the minus X when the concentration of something is greater than the number of sig figs. I don't
Okay,
quite remember.
close.
It had something to do with
Close.
sig figs and concentration.
Okay, okay. How about 10 to the number of sig figs?
Yeah.
There we go. And then the concentration of this thing, does it just live there by itself?
No, it's above K.
There you go. Perfect. And just a reminder, this is an important thing. This is the initial concentration of my acid or my base. So is this a Ka? Tannen? Am I doing an acid reaction?
Not really.
Yep, nope. So I can't use Ka. This has to be, actually, let's just do that. Has to be Kb. Right, I'm producing hydroxide. That means my fluorine atom or ion is acting like a base. So if it's acting like a base, this whole thing has to be in terms of a Kb.
Oh, and spoilers. You can ignore the negative X.
You already looked
Because
at
I
that?
got KB equals 1.515 ... times 10 to the negative 11, which is way more than the number of 10 to the number of significant figures.
So how did you get your Kb?
I did it by having 1 times 10 to the negative 4 and dividing it by the Ka.
Good, so you did this, that my Ka times my Kb equals
Yeah.
what?
Equals Kw.
Good, perfect. And that it just comes from this expression, because remember, I'm going to have like this Kw equals the concentration of OH and the concentration of H3O plus. And another way of looking at that is that this is Kb and this is Ka. So I can write them, my Kb is going to be my Kw, so 10 to the negative 14, divided by my Ka, 6.6 times 10 to the negative 4. And then my trick for simplifying that negative 4, another way of writing it is 10 to the 4th. So I'm going to have 1 over 6.6 times 10 to the negative 10. And so what did you get for your Kb? It's going to be like 10 to the negative 11 something.
1.515151515.
Times 10 to the negative 11.
Yeah.
Okay. And that is my Kb. So now for, can I ignore X? Ignore my minus X. what do I have? My initial concentration is that 0.5. With, yeah, I'll go ahead and write the whole thing out. Divided by 1.5 times 10 to the negative 11. The other way to write that is that I'm going to have like 0.5 divided by 1.5. And that 10 to the negative 11 is going to come up. And I want to know if this is greater than 10 to the, there's 2 sig figs here, so 10 to the 2. Now I'm going to have 0.5 divided by 1.5. So this is going to come down to like 10 to the 10. But without button pushing, even if it went down to 10 to the 9, that is greater than or equal to 10 to the 2. So I can ignore X. And the reason why I want to emphasize that is I don't want you to get bogged down in using your calculator for everything. You can generally just move this around and make an ish approximation about what's happening with everything else. And it's going to generally be either much larger or much smaller than what you're looking for. If it's close, then you want to button push it. So is that part clear to everybody?
Yeah.
Cool. So then I'm going to have KB equals what? What's my expression for KB? Sean. What is my equilibrium expression? Or equation? Sean?
Sorry, I kind of missed the first half of that.
What is my equilibrium expression for KB?
For KB. Not super sure.
Annie?
HF times OH over F times H2O. Wait, no, don't include H2O. It's just F.
Perfect. Perfect. And is anything raised to an exponent?
No.
Perfect. Yeah, there's no coefficient in front of that. So then I can turn around and write this in terms of my x's. If I'm ignoring my x's, I'm going to have x times x divided by, I'm ignoring the minus x portion. So divided by 0.5.
I'm sorry, why didn't we include water in the bottom again?
Because it is a different phase. So,
Okay, thank you.
You're welcome. You're welcome. No, I'd much rather you ask those questions. That just helps solidify it for everybody. So then I'm going to have x squared over 0.5. And finally, we can solve that x is going to be the square root of 0.5 times my KB, which is my 1.515 times 10 to the negative 11. Does anybody put that in their calculator yet? Okay, I'll put it in my calculator. 1.555 times 10 to the negative 11. And I get 2.75 times 10 to the negative 6. So is X my hydroxide concentration? Sean? Change screens and feel like I'm calling on the same people. Hannah?
When I was working on the smart work yesterday, I kept mixing these up.
Okay.
I believe it's your OH, right?
Yeah, so it's actually,
or is it your H3O?
Well, what, okay, to answer your question, what is in this reaction? This is what we were solving for our KB on.
Yeah. I kept mixing these up in my smart work. Like I got the right answer, but I kept mixing up if it was my POH or if it was my pH.
Okay, so I haven't asked for the pH or the POH yet. So first, let's come back to that and make sure that you're comfortable with it before we finish the lecture today. What does that X value represent? So I have X equals 2.75 times 10 to the negative 6. Anyone?
It'd be the HF and at least part of the OH, depending on how much is from the ionization of water.
Yeah, and notice this is actually fairly close to the 10 to the negative 7 from the ionization of water. Ionization. So the one thing I can tell you, at least through Monday, is we're not going to go through and redo it. It is going to have an impact, but a relatively small impact. But when the things are that close, when I'm 1 order of magnitude off, to be correct in my pH prediction, I would want to go back through and change this one to my starting point of autoionization of water. But for now, okay, plus X means that I know what my concentration of my HF is and my hydroxide. For pH, I can't use HF.
I had a quick question.
Yeah.
Sorry, just before we go on. If you put in the initial OH concentration, then you'd have whatever that concentration is plus X for the
and then you're doing a
equilibrium.
quadratic.
Yeah, so with that, can you do the thing where you ignore plus or minus X, or can you not do it with that?
No, and thank you for asking that. The reason we can't is, let's go back to how we checked that. My initial concentration here would be 10 to the negative 7. Right? So I'm going to have 10 to the negative 7 divided by 10 to the negative 11. So 10 to the negative 4. Yeah, by our rules, we technically can, but it's going to be really close. It's not anything that you would lose points for. How's that? So if you did this division and said that number is slightly greater than 10 to the 2, therefore I'm not going to consider the 10 to the negative 7. At this stage in the game, nobody would get dock points for that.
Okay, awesome. But that's not something we really need to do right now.
Yeah, but in real life, we would.
Okay.
Yeah. Is everybody good with that? Okay. So for my pH, can I use my hydroxide concentration? So remember, pH equals the negative log of what? Rory.
Yeah, sorry, what?
pH equals the negative log of which concentration?
Of the concentration of the acid. So let me put that in a calculator real quick.
Of HF?
Do we have the concentration of OH or no?
We have the concentration of OH. That's what we solve for with our X.
Okay, cool. I wasn't sure if that was the concentration of HF or not.
Yeah, so it's also the concentration of HF, but is POH and pH, are they specific to hydroxide and hydronium, or are they specific to like whatever acid or base we have in solution?
For pH, I got 8.44 because I did 14 minus the negative log of 2.75 times 10 to the negative 6.
Okay, good. So why not use HF? Just do like pH of the at 2.75 times 10 to the negative 6.
Because it's a weak acid.
Yeah, thank you. And so I wanted to make sure that is clear, because it's very tempting to say, well, I want the pH of the concentration of the acid. So therefore, if I know what HF is, I can just do pH of it. Remember, pH is only, make it a sticky note and highlight the darn thing and put it on your computer, only of H3O plus. And POH is only of hydroxide, so my OH minus. Those are the only two species that will give us pH or POH. Is that part clear with everybody? And then Rory with, I'm sorry? Did I have a question?
It's clear to me.
Okay. So there's my pH, my POH is negative log of the concentration of my hydronium. And then what
which got me about sorry for interrupting, which got me 5.56 POH.
Oh, I got the pH. So at 8.43E97133034 for pH.
Okay, so 14 minus the pOH, in other words, right?
Yeah.
Cool. And you got what again? 8 point something or other?
Yeah, 8.4397.
Just 4.
Okay, so let's talk sig figs real quick, and we'll come to common ion effect and the Henderson-Hasselbalch buffers on Monday. But
That
what I
would
want to
just
know,
be 8.44.
good, why? How did you decide that?
Because you would round up the to 2 decimal places.
Okay, why?
And the last decimal is 3, and the decimal after that would be a 9. So then it would be rounded up.
Okay, so how did you choose your 2 decimal places?
Through the significant
Run with it. Run with it.
figures of the concentration.
Yes, my concentration is going to have 2 after the decimal.
Yeah.
Right. And so when we go our pH and pOH, it's how many after the decimal of our concentration. That is what contributes to our sig figs on our pH and pOH. Is everybody good with that? Okay, stop sharing and stop recording.